Okay, and now we will discuss, so we will start with the lecture. It will be lecture number 8.
What if my solution doesn't have a parameter?
So I will check and you will see the results in the table of results. Now I can't decide what to do with this. Well, today we will discuss linear differential equations. So I'd like to formulate linear differential equations of order n. Let it be the general title, but we will consider a particular case. Okay. So linear So this is a very wide and so it is a very deep and wide topic, and today we will consider a particular case, but some statements will be general, but at the end of the lecture we will consider only a particular case. We will consider linear differential equations with constant coefficients, and the second requirement or so restricted, we will consider homogeneous linear differential equations with constant coefficients. But we will start with some general statements. And first of all, we will consider for maybe 2 or 3 lectures, we will consider linear differential equations of order n. What does it mean? So we will consider the equation of the following type. The coefficients, so it will be of this form. So we will consider a function, some continuous function, which doesn't vanish at any x on some interval I. So x will belong to some interval I. Fn of x is a continuous function which doesn't vanish at this interval, times the nth derivative of y plus fn minus 1 x times y, the n minus 1. So the derivative of order n minus 1 of y plus and so on, plus f1 y prime plus f0 of x. Okay, today we will discuss homogeneous linear differential equations. So this means that, okay, not this, times y equals 0. Homogeneous equation. So this equation is linear because all the derivatives of y are raised to the power 1, right? And it is homogeneous because the constant term, so the function which is not multiplied by y is equal to 0. Okay, and so we will need statement number 1. So all the functions must be continuous. So the functions on I. And we will need the following statement, so the following theorem. So if functions, let's call them let it be y1 of x and y2 of x are solutions to this differential equation. Then their linear combination, any linear combination with any constant c1 times y1 of x plus c2 times y2 of x is also a solution.
The solutions of these equations generates a linear space?
Yeah, right. So vector space, it is called, in English it is vector space, right? Generates vector space, right, correct. So if we consider we can consider the vector space of infinite dimension, right, and the vector space of continuous functions, right? And if we consider the functions, I think not continuous, but differentiable functions, so we need to be able to find their nth derivative, right? And this will be the subspace of the space of all the functions, right? Because the linear combination of any solutions is a solution. And so we will need this statement. It is not difficult to prove, but we will use it in what follows. So let's prove. So the proof is not difficult. Since y1 is a solution, then it satisfies the following. Fn of x times y1, the nth derivative, plus dot 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 plus f1 of x times y1 prime plus f0 of x times y1 equals 0. And at the same time, y2 is also a solution. And so we have the following. Fn of x times y2, the nth derivative, plus f1 of x times y2 prime plus f0 of x times y2 equals 0. So both functions satisfy this differential equation. And if we multiply the first one by c1 and the second one by c2 and find the sum, so we will get the following. Fn, and if we combine similar terms, we will get the following. Fn multiplied by the nth derivative of y1 plus the nth derivative of y2 plus and so on, plus f1 y1 prime plus y2 prime plus f0 times y1 plus y2 equals 0. Okay, and multiplied by c1 and c2. So I have forgotten the constants. C2, next C1 plus C2y2, C1 plus C2y2. And you can see, so it follows that C1y1 plus C2y2 is a solution. So theorem is proved. And the corollary is that any linear combination of any set of solutions is also a solution, right? By induction on n, we can prove the following corollary. So corollary if y1 and so on, yk are solutions, of the original differential equation, then their linear combination is also a solution. Well, so maybe do we need a break? Okay, it turns out that a homogeneous linear differential equation of order n has as many linearly independent functions as the order of this equation. So this will be discussed next time, so on the next lecture. But now I'd like to discuss the following problem. So we need to know n linearly independent solutions to form a general solution, and an n parameter family of solutions will be formed using this corollary, right? So now our goal is to find n linearly independent solutions to this linear differential equation, homogeneous linear differential equation of order n. And so today we must discuss the problem of finding, not finding linearly independent solutions, but the problem of checking whether the given set of functions is indeed linearly independent set, right? So now we will discuss linearly independent functions. So we will work on the interval I. So x belongs to I, and we are given the set of functions fn of x, and we will start with the definition. The set of functions f1 of x dot 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 fn of x is linearly dependent first, right? Dependent. If there exist constants C1 and so on Cn that are not all zero, such that the following linear combination, so f1 of x, so C1 plus C2 f2 of x, the linear combination of these functions with these coefficients is identical 0 for any x from the interval. So linearly independent. The set of functions is linearly independent, so otherwise, if we can't find the constants such that this linear combination is 0. Fn are linearly independent if there are no such constants. Now the question is how to check whether the given functions are linearly dependent or independent. And we will start, first of all, we will consider the examples in order to see linearly independent functions and linearly dependent functions. So we will try to solve this, to answer this question, so by hand, I think, without any machinery, right? Without applying some complicated technique, right? So example 1. Let's consider the following functions. F1 equals, let it be x. F2 is minus 2x. F3 is, let it be 3x. And let's check whether these functions are linearly dependent or independent. So we can consider the entire real line for I. Okay. Let's use the definition. So we are looking for the constants such that C1 times x plus C2 times minus 2x plus C3 times 3x equals 0 for any real x. If we regroup, if we expand and regroup this, we will get the following equation: C1 minus 2c2 plus 3c3 times x equals 0. Okay, can this equation be satisfied identically for some values of c1, c2, and c3? Of course, yes. So we need to solve the following linear homogeneous equation equals 0. It has infinitely many non-trivial solutions. For example, so the example will be, so I will start with C3. Let it be C3 equals 1, for example, C2 equals 1, and then C1 equals 1. Well, not 1, minus 1, negative 1. Okay, so it is satisfied, for example, for so with these constants, with these values. Okay, so the answer is this set of functions is linearly dependent. Let's check the other functions. Let's consider the functions. Let it be f1 equals x to the power p and x to the power q, and I will be x greater than 0. And p is not equal to, so doesn't equal q. Okay. And this is f2. So f1 and f2 equals x to q. Let's check whether these two functions are linearly dependent or independent. So let's try to solve the following equation. C1 times x to p plus C2 x to q equals 0. And this equation should be satisfied and identically for any value of x. Okay. So let's substitute something, maybe, or it can be solved generally, maybe, so I will not, or maybe substitute something. Let's substitute x equals 1, and then we have the following: C1 plus C2 equals 0. And let's substitute x equals 2, and we will get 2 to the power p times C1 plus 2 to the power q times C2 equals 0. And if we divide by 2 to the power p, for example, we will get the following: C1 plus 2 to the power q minus p times C2 equals 0. So these simultaneous equations so this set of two simultaneous equations has only trivial solution. right? C1 plus C2 equals 0. This means that, for example, C2 equals minus C1, and if we substitute it here, we will get so on substituting this into the second equation, we will have the following: C1 times 1 plus so minus 2 to the power q minus p equals 0. But this factor is not 0 because p is not equal to q. So this is not 0, and this means that C1 is 0. So these two functions are linearly independent. Linearly independent. Likewise, we can show that the functions, for example, e to the power px and e to the power qx are linearly independent. So in the similar way. And the last very important example will be, let's consider the following functions. Let it be, for example, x, then 0 and e to x. If one function is 0, what can we say about the set of these functions? Is it linearly dependent or independent? What is your opinion? What is your idea? Right. So we seek the following, the non-trivial solution of the following equations: C1 times x plus C2 times 0 plus C3 times e to x equals 0. And if we look at the second term, we can see that C2 is multiplied by 0. So it's always 0, and it doesn't depend on the constant C2. And so if we take C2 to be equal to 1, and so C1 equals C3 equals 0, then this equation will be satisfied with these constants. So if the set of functions contains 0 as a function, then this set of functions is linearly dependent, of course. So linearly dependent. But we want an algorithm to answer the question how to check quickly is the given set of functions linearly dependent or independent. So not by hands, right? So it's the complicated procedure, right? But if we're given if we are given many functions, right, so we need to have an algorithm how to check this. And so it will be given by the Wronskian. So now we will need the Wronskian, the theory of Wronskians, and so I will discuss it. First of all, I will introduce some determinant. It is called the Wronskian. It is called after the Polish mathematician Wronski, so named after Wronski. Polish mathematician, and the definition is as follows. Given a set of functions, let f1, f2, and so on, fn be a set of functions, having the derivatives up to order n minus 1. Then we can form a matrix, and the determinant of this matrix will be called a Wronskian. F1, it is denoted by W capital of F1 and so on, Fn and X, and it is equal to the following determinant: F1 of X, Fn of X, and then goes derivatives, the first derivatives of these functions, dot, 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 and the last row will be the n minus, the derivatives of order n minus 1 of X. So this determinant is called the Wronskian, so is called Wronskian of the set of functions. Well, and in what follows, we will need the following theorem. So it's theorem number 2. If the set of functions is linearly dependent, is linearly dependent, okay, for maybe let it be for on some interval I, then the Wronskian is what? Do you know? Is equals 0, right? Is vanishes identical 0 for any value x from I. Okay. Let's prove it. Suppose the functions are the set of functions is linearly dependent. This means that there exists constants such that C1 F1 plus C2 F2 plus and so on plus Cn Fn equals 0 for any value of x from the interval. So vanishes identically. Then let's differentiate this equation. Let's take the derivatives of all the functions, but let's differentiate the both parts of this equation, but using the linearity of derivatives, right? We can represent it in the form C1 times F1 prime plus C2 F2 prime plus dot 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 plus Cn Fn prime equals 0. We can differentiate this several times up to the the derivative of order n minus 1 plus C2 F2 of order the derivative of order n minus 1 plus so on plus Cn Fn n minus 1 equals 0. Okay. If we fix any x, so now fix fix x. For x fixed, we can consider this set of equations. So as follows. So we have n equations, and f1, f2, and so on, fn are constants now. If we fix x, then all the functions at this given fixed point are constant, right? And the derivatives are also constant. And the n minus 1's derivatives are also constant, right? So we can consider this system of linear as the system of linear equations in the parameters C1, C2, and so on, Cn. We want to find so suppose we want to solve this linear equation with the constant coefficients F1, F2, and so on, and we want to solve this system for C1, C2, and so on, Cn. So if we know that these functions are linearly dependent, then we know that there exists a non-trivial solution of this linear system. So this is a non-trivial solution. A non-trivial solution of this linear system. But from linear algebra, we know that existence of a non-trivial solution can be interpreted in terms of the determinants, right? If the so the linear system of homogeneous equations has a non-trivial solution if and only if the determinant of coefficients is equal to 0. So has a non-trivial solution if and only if the determinant, but the determinant is just the same as the Wronskian, right? The determinant F1, F2 of the matrix formed by these functions and their derivatives is 0. Okay, since this is true for any x fixed, then it is true identically. So this determinant vanishes identically on the interval I. So theorem is proved. Okay. Unfortunately, this is only the necessary condition for being linearly dependent. So this theorem works as follows. If we know that, if we can compute the determinant, so given n functions, we can compute the Wronskian for them. If the Wronskian is not 0 at some point, then it follows that these functions are linearly independent. So because we know that, so this is the logic. If they are linearly dependent, then the Wronskian vanishes identically. Then, if we know if there exists x on I, for which the Wronskian is not 0, so the negation to this statement implies the negation of this statement, right? So if we know that there exists x for which the Wronskian is not 0, then the functions are linearly independent. Independent. Okay, let's try to apply this statement for some functions, for the functions, the set of functions. So example 2. We will start with the Wronskian, with computing the Wronskian for two functions, f1 and f2. It will be f1, f2, f1 prime, f2 prime, and it is equal to f1, f2 prime minus f2, f1 prime. Let's use the theory of Wronskians to check that the functions e raised to the power px, let it be lambda 1x, and f2 equals e to lambda 2x are linearly independent. On R. Let's form the Wronskian. It will be e to the power lambda 1x, e to the power lambda 2x. Then if we differentiate these functions with respect to x, we will get lambda 1 e raised to lambda 1x, lambda 2 e to lambda 2x, and the determinant is equal to e to lambda 1 plus lambda 2x times, this will be the common factor, it will be lambda 2 minus lambda 1. So if lambda 1 is not equal to lambda 2, then the Wronskian is not 0, because this never vanishes, this factor never vanishes. And lambda 2 is not equal to lambda 1, then this Wronskian is not 0. Okay, but this is not maybe so interesting. We may check that these two functions are linearly independent by hands, right? It is not difficult, but given n functions of this type, so it will be more complicated. And let's consider this example. Now we will discuss two important examples. Example number 2, given n functions, e to lambda 1x, f2 equals e to lambda 2x, and so on, fn equals e to lambda nx, where lambda 1, lambda n are different numbers. Let's check that these n functions are linearly independent. If we let's form the Wronskian, it will be e raised to lambda 1x, e to lambda 2x, and so on, e to lambda nx. Then the second row will be lambda 1 times e to lambda 1x, lambda 2, e to lambda 2x, lambda n e to lambda nx, dot, 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 and the last will be lambda 1 to the power n minus 1, lambda 1x, let's discuss the determinant. Right, right. So, first of all, let's consider this column. All the entries of this first column have the same factor, e to the power lambda 1x. So it can be moved through the determinant sign using the properties of the determinant. So it is equal to e to the power lambda 1x, right? I will leave the space. So the first column will be 1, lambda 1 squared, and so on, lambda 1 to the power n minus 1. Next, look at the second column. So we can do the same. So we can move the factor e to the power lambda 2x out of the determinant sign. And so the second column will be 1, lambda 2 squared, and so on, lambda 2 to the power n minus 1. Dot, 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 e to the power lambda nx. And the last column will be this, lambda n to the power n minus 1. Okay, do you know this determinant? Right, Vandermonde determinant, right? It is not 0. For different values of lambda, it is not 0. It was proof in the course of linear algebra, right? So this proves that these functions for different values of lambda are linearly independent. And I will consider the last example. Let's consider the functions 1x, x squared, and so on, x to the power n minus 1 on R. And let's form the Wronskian of this function from this functions. The second row will be, we differentiate them, it will be 0, 1, 2x, and so on, n minus 1, x to the power n minus 2. Next will be 0, the derivative of the 0, 0, 2. Okay. And the last row will consist of zeros, and the last term will be n minus 1 factorial. Let's find the determinant of this matrix. It is equal to the product of the entries on the main diagonal. It is equal to 1 times 2 times 3 factorial times, and so on, times n minus 1 factorial, and it is not equal to 0. So these functions are also linearly independent. Okay. Now, maybe I'd like to continue my lecture a little bit after the break. Let's have a break, and I will finish my lecture because I need to reach to the solutions of differential equations. Right? Let's have a break. Now I need time to finish the lecture. Stop talking, boys. Let's get started. Right. Now we will consider homogeneous linear differential equation with constant coefficients. So homogeneous differential equation with constant coefficients. So now we return to our differential equations. And we will start with the equations with constant coefficients. This means that we will consider the equations of the form. So an is a constant, a non-zero constant. So an is not zero. So when x, is a non-zero constant, right? So an multiplied by the nth derivative of y plus an minus 1 is now not a function but a constant multiplied by y, the derivative of order n minus 1 plus and so on plus a1 times y, so a0 times y prime plus a0 times y equals 0. We will consider a homogeneous linear equation with constant coefficients. an and so on, a0 are constants. And we are looking for linearly independent solutions of this homogeneous equation, and we need to know to find n linearly independent solutions. Then we will take a linear combination of them, and we will get the n-parameter family of solutions. Right? So we need n linearly independent solutions. And so by guess, right? So we will look for the solution in the form y equals e to the power lambda x. So we guess that our solution will have this form. Let's try to substitute it into our differential equation. We need to take the derivatives of y, and we will get, so y prime will be equal to lambda times e to lambda x, dot, 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 and the case derivative will be lambda to the power k times e to lambda x. And now on substituting this into the original equation, we will get an times lambda to the power n e to the power lambda x plus an minus 1 times lambda to the power n minus 1 e to lambda x plus dot 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 plus lambda e to lambda x plus a, so just a moment, plus a1 and plus a0 times e to lambda x equals 0. We can see that e to the power lambda x is not 0 for any value of x, and so we can divide by this non-zero coefficient. And on dividing, we will get the equation, the following equation: an times lambda to n plus an minus 1 times lambda to the power n minus 1 plus dot 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 plus a1 times lambda plus a0 equals 0. Okay, so we want this function to be the solution of this differential equation. Okay, and so we can see that any lambda satisfying this polynomial equation will make this function a solution of the original differential equation, right? So our task is to find the solutions, the roots of this polynomial equation, the roots of the polynomial. This equation is called the characteristic equation of our differential equation. So it is a definition. It is called the characteristic equation. Okay. By the fundamental theory of algebra, fundamental theorem of algebra, says that any polynomial has n roots regarding the multiplicity. So they may, some of them may coincide, and or they may be complex, maybe, right? But it has n roots. This is just what we need. Right? And now we will consider several cases. So the simplest case, it will be considered on this seminar, and next cases will be on this lecture. And next cases will be considered later, after a week. So the first case is when there's characteristic polynomial has an different real roots. Case number 2 to be considered is when Pn of x has real roots, but they can be, some of them can be multiple roots. Maybe multiple. So with multiple roots. And after all, we will consider the case when Pn of lambda has complex roots. So has roots, some of which are real and some of which may be complex. Has complex roots. So real and complex roots. The most general case. So today we will consider the first case when all the roots are different. So case number 1. The characteristic polynomial has roots lambda 1 and so on, lambda n, which are different numbers. Then we can see that all the functions lambda 1x, y equals e to the power lambda nx are solutions because they satisfy the character. So lambdas satisfy the characteristic equation. Then it follows that these functions satisfy the differential equation. And so first we know that they are solutions. And second, computing the Wronskian of these functions, we can prove that they are linearly independent. Therefore, okay, and so applying theorem number 1, we can obtain the n-parameter family of solutions by theorem number 1, proved today in the beginning of our lecture. Any linear combination of these solutions is also a solution. So the general solution will be given by the linear combination of these functions with some coefficients, any coefficients, right? C1 times e to the power lambda 1x plus C2 e to the power lambda 2x plus so on plus Cn e to the power lambda nx. Well, and let's try to solve, to find the general solution of some concrete equation. So task number 1, so it will be the example to this first case. Find the general solution of the following equation. y3 primes plus 2y2 primes minus y prime minus 2y equals 0. Okay. Right. So this is our differential equation. So step number 1, to form the characteristic equation. So we should replace y3 primes by lambda cubed. Next goes 2 lambda squared minus lambda minus 2 equals 0. And next we should try to solve this cubic equation. Do you know how to solve? There are no formulas for, there is a formula, but it is too complicated for the roots of the cubic equation. But
I love the roots.
right, so we should guess the root, right? And after this,
we can guess one of the roots, and from that we can obtain a quadratic equation.
right, of course, yes, yes, So first we will start with guessing the root. So lambda equals 1 is a root, right? So this means that if we divide this polynomial by lambda minus 1, so this polynomial is divisible by lambda minus 1, and so let's divide and find the quadratic polynomial, and after this we will solve it. Okay, so lambda squared, lambda cubed minus 2 lambda squared, 4 lambda squared minus lambda plus 4 lambda so no, just a moment. Something. So lambda, right? So 1 cubed plus so lambda squared minus lambda squared, right? Minus not lambda, not 2, but 3, right? Minus. This one is so 3. 3. Okay. Next, if we subtract, we will get 2 lambda minus 2, so plus 2. So we have a quadratic polynomial. And we need to know the roots. We may use that discriminant formula, or we may as well guess. So I can see that the other root is -1. -1. So it's lambda 1, lambda 2, and lambda 3 will be, so -1 and so -2. So the product must be equal to 2. Right. Okay, so we know the roots. And now step number 2 is to write the answer. Just write the answer. equals C1 times e to the power, so we should substitute 1 for lambda 1, so e to the power x, right? Next, plus C2 e to the power negative x plus C3 e to the power 2x. So this is the general solution. 3-parameter family of solutions, right? And after this, we will consider the last example. I will use that part of the blackboard. Example number 2 will be the following. Find the particular solution. So the particular solution of the equation, differential equation 1 to y2 primes minus 3y prime plus 2y equals 0, satisfying the following initial conditions. Y of 0 equals 1 and y prime of 0 equals 0. Let's solve the initial value problem. So we will start with the characteristic equation, lambda squared minus 3 lambda plus 2 equals 0. What are the roots? Is it easy to guess the root? Not. So negative 1, so plus, it's plus. Then 1. 1 is a root. And lambda 2 is equal to 2. Okay, so this is the first step. And then the general solution will be given by y equals c1 e to the power x plus c2 e to the power 2x. This is a general solution. And after this, we will use these initial conditions to find a particular solution satisfying these conditions. Okay, so we need to substitute 0 for x and 1 for y, and we will get the first equation. It will be 1 equals c1 e to the power 0 plus c2 e to the power 0. But we need the second equation in c1 and c2. To obtain it, we should use the second condition, right? To use it, we must differentiate this solution. Y prime is equal to c1 e to x plus 2c2 e to the power 2x. And substitute 0 for y prime and 0 for x. And we will get the following. The second equation equals c1 plus 2c2. We must solve these two simultaneous equations. It's the same as c1 plus c2 equals 1 and c1 plus 2c2 equals 0. Okay, if we subtract, we will get c2 equals negative 1 and c1 equals 2, if I'm not mistaken. Well, it's this. And so answer. Our particular solution is given by the formula 2e to x minus e to 2x. This is a particular solution satisfying these initial conditions. Okay.